Thanks a lot to our panelists, and thanks a lot to Philip for navigating through this first exciting panel. As he already mentioned, feel free to use the Q&A opportunity right now. And there's lots that needs to be done, and there's a lot of opportunity for exchange, not only for our participants, but also for you as our audience. So feel free to check out our partner area, where our partners Atos, Fujitsu, and Fraunhofer will be happy to answer your questions. And in case you haven't noticed, there is also a second stage, and even though I'd be really sad to say goodbye to you, feel free to also check out our second stage. And having said that, what I really loved about the panel is that we had a philosopher on our panel, because obviously when we look at the quantum community, it's closely knit and there's a lot of physicists there. And we need to widen the range of people being engaged in this dialogue. And that's why the following panels and the following inputs will be focusing on education. So from SMEs and startups, we go back into academia, and our next panel and our next input has the headline Educational Models for Teaching Quantum Computing to Applied Science Students, because in order to build up the labor force that is educated in quantum computing, we need to find suitable education strategies. And one that is really knowledgeable about that, he's coming from the Technical University of Applied Science in Ingolstadt and will be sharing his learnings and best practices, is Professor Ulrich Margol. He's the professor for embedded systems and computer engineering, and he's the Dean of Didactics and Student Issues in the Faculty of Computer Science. And we're really thrilled to see your stance on what exactly needs to be done to educate the next generation of quantum computing specialists. The stage is yours.
So thank you very much for the nice introduction. And it's a great pleasure to be here on the Quantum Summit to see all these new technologies coming up and the new strategies being developed. My focus here on this talk is a little different, because I'm not focusing on what new technologies we have. I'm focusing on the people in the field, the computer scientists that will be working in the field in some years. And when we want to have quantum computing a big thing in the future, we need people that know how to handle this. And my talk is about educational models for teaching quantum computing to applied science students. I myself am a physicist. I studied physics at the University of Regensburg and made my PhD there. But then I went into software industry, worked in industrial practice and software development in large systems, database systems, internet streaming technology, and lately, the last 10 years in embedded systems, mainly in the automotive industry. Since 2012, I'm teaching and researching at the Technische Hochschule Ingolstadt. And for some years now, I'm a Dean for Education and Student Issues at the Faculty of Computer Science, which is a German Studiendekan. And my talk is about teaching normal students quantum computing so that we have enough knowledge in the field in practice. So what does it mean, students? If you look at students in Germany, over the last 20 years, we see a strong increase. And the last years, we have around 55% of all young people starting a academic study program. So this is quite a lot. This is more than half of all young people start at university. And about 1/3 of those start in a STEM program. This means science, technology, engineering, or mathematics, or MINT, as we call it in Germany. This is a lot of people that are going into an academic program, but as we all know, not all of them finish successfully. We have dropout rates. We are working on these dropout rates. We try to improve our programs, but in the end, not everybody is capable of doing an academic program. Where do these students go? If we look again in the numbers in Germany, we see that about 60% of those students go to a traditional university, a blue area here, while around 1/3 of all students go to a University of Applied Sciences, a Hochschule. So the profile of a Hochschule is a more application-oriented, more practical, and less theoretical. So when we have a teacher at the University of Applied Science, he is required to have some industrial background, so 3 to 5 years of industrial practice. And if you look at the students and the student programs, in the bachelor, we have a 4 months internship, which is mandatory for all students. So they know how while studying, they go to industry, they work in their field, for example, computer science, and make first-hand experience. And also the education is directed towards the industry. So we are focusing on practical competencies. We have a University of Applied Science, typically are in the field. We have many of them in Germany, and they have a strong relation to local companies. And here, especially the small and middle enterprises, because a big enterprise is worldwide active and they can have contact to any university worldwide. A small company has typically only contact to the near universities that are in the region. Universities of Applied Sciences often also provide professional trainings for SME employees. So there are programs where small companies can build and train their workforce and improve the knowledge on the people. And University of Applied Sciences directly prepare for careers in industry. So like automotive, avionics, and all other industries. And a bachelor student from a University of Applied Science is very well seen at a industry. If we look at those students that come to our university, and we have a profile that around 1/2 of them, the blue half here of this circle, has a traditional high school degree, Abitur, while the other half has a secondary education path or even an industrial background. So we have people working in industry and then coming to our university, like the Meister program in Germany. And this means that our student qualification is quite heterogeneous. We have high potentials, we have research ongoing, we have PhD programs, and we have the students for these programs. But in the overall, students is a broad range of competences. And as I said before, we have also significant dropout rates in the program. So if you want to teach these people, it's not about teaching the high potentials like what we discussed in this quantum summit here, the new future of quantum computing. It's about teaching the broad mass of the students something about quantum computing so that in 5 or 10 years, there is a knowledge around in the industry on a broad range. How can this be done, or what are the challenges here? If we look at computer science, a classical computer science program, we have technical aspects like programming, computer hardware, networks, algorithms, and data structures, and so on. This is from the curriculum of computer science at THI. This is what we are teaching to our students. And we have non-technical issues, which are also very important in computer science, like mathematical foundations, because we need mathematical topics everywhere, but also skills like project management, software engineering, requirements engineering, computer ethics, and also business management, entrepreneurship, which is mandatory for a successful career in the industry. And now we want to add quantum computing to our program. And if you work on a teaching program, the problem is not what you put inside of your teaching program on your curriculum. The problem is what you leave out of your curriculum. And it's like a bottle that's filled with water. If you want to put something new in, we have to remove some other stuff. So this is a hard choice because adding quantum computing means removing something else. What could this be in quantum computing that we need to teach them? If we look at the history of quantum computing, in the second half of the 20th century, the conception and fundamentals of quantum computing have been defined. We've heard before from Jan Götz that in the 1965s already the first principles were laid. Feynman came up with his ideas about quantum computing. Algorithms have been defined. And today we have evolved and we are on the bridge of useful applications. So this is the situation today. We have a promising approaches to quantum computing, and sometime in the future, we will have quantum computer available for industrial applications on wide scale. So this is the idea. This is what we are discussing here on this summit. But what does this mean? What exactly are the technologies? What exactly are the qubits? Do we have better error corrections? Do we have new algorithms, new applications, new protocols? How will this future look like? And as a teacher, I'm teaching students maybe age of 20, 25, and they will be in industry for 30, 40 years. So the question I always have to reflect myself is, what can I teach my students now that helps them the next decades to perform in their job? So the question here is, or the challenge is that we are teaching for an uncertain future. This is clear for traditional fields, but especially for quantum computing. And I've taken out some aspects of the teaching. One is the competencies that we want to teach. And here I have taken the Bloom taxonomy about different competencies from just bare knowledge, I know something, until over comprehension, I understand what this is. Application, I can apply this to a standard problem. And then the higher competencies like analysis, I can apply it to new problems. Synthesis, I can derive new aspects, new strategies out of my knowledge. And if we think about quantum computing and a normal student of computer science, we have to focus on the foundations. These are the lower levels. And if we look at concrete problems that we have, for example, mathematics, if you look at computer science, you don't find complex numbers. They are not really used in computer science. You have a lot of discrete mathematics, you have probabilistic approaches, and you might even have some quaternions in graphics, computer vision. Quaternions are four-dimensional numbers, but complex numbers are not used in computer science, and our students do not really know complex numbers. They have heard of them, but they are not into these numbers. So this is something we have to teach them, at least the concept that's behind this. The same applies to matrices or tensor products. They are in computer science, but our students do not work with them on a daily basis. So we have to teach this know-how. And also quantum mechanics. We have some physics education in the program. We have some basic physics, but quantum physics is not really part of it. But we need to teach them at least some aspects of quantum nature about photons, qubits, and single atoms. And if I look at certain aspects of the teaching that we do, we have a stack here, some aspects of a stack. We have a computer hardware, we have operating systems, we have applications, and we have an algorithmic layer. And on the computer hardware level, we have for 50 years now basically the same. We have transistors, they are just switching elements. We have zeros and ones. We have a Boolean algebra below it. And then our computer architecture with processors, memories, pipelines, caches. This is what our students know. This is what they need to know. We have a hardware abstraction in the operating system where we have processes, file systems, communication stacks. And then we have the application, creation of applications. Here our students are confronted with IDEs, compilers, linkers, frameworks, tools, and very important development processes, quality issues, and stuff like this. And also another layer is algorithms and algorithmic complexity. But if I go to a student and tell him he needs to sort some data, what he typically does is he just takes a framework and calls a sort function. But we teach them the complexity. If I compare this to quantum computing, what do we need to teach for quantum computing? On the hardware level, we have to discuss about how much quantum mechanics is needed. We have qubits, not bits. So qubits is a completely different thing, and this is something we have to teach our students. On the runtime environment, we have to teach them how to run quantum applications, how communication can look like, and how a storage of quantum information can look like. Applications, here I see less change. With quantum computing, we have just another IDE, we have just another framework, and we have development processes that are maybe different, but not really a complete different thing. And again, on algorithms, here we see a big changes in quantum algorithms and the applications that our students need to understand so they can apply the technology. Wrapping this all up to a conclusion, we need to think about what curriculum, textbooks, and teachings we can teach to our students on a broad scale, not to create the new brilliant high potentials that bring quantum computing forward, but to the broad field of to the masses of our students so that they can cope with quantum computing once it's in industry in 5 or 10 years and they see it in their daily life. So what is needed here? What of the quantum information concepts are really necessary for them? They are not physicists, they do not study quantum mechanics, but they need some understanding of the fundamental aspects here. What we already teach them is large computing resources, HPC or quantum or cloud computing. And here quantum computing comes in as a new aspect with an eye towards the risk of those technologies. And what we need is a network for teaching applied quantum computing and quantum information. And here I can give a link to the project Quantum at HAWEN and also the project HAQUA that will probably be presented later on stage, Alice, by my colleague Bettina Just. So I think this is a more grounded view, not the high-flying concepts we've seen here up to now, a more view of the normal students' view on quantum computing. And thank you very much. And I hope I could give you some aspects from a daily teacher's life. And if you have any questions, I'm available and I will be available afterwards on the stage room.
Very much, Professor Margul. This was really an interesting insight into the basics of how quantum computing might be taught or taught in the future. And again, we have around 1.5 minutes left. So if there are any questions from the audience, I highly encourage you to do that. Maybe one direct question to you, as our next forum is looking at the European perspective. When it comes to teaching methods, teaching strategies, are there any countries, any best practices where you say, yeah, it would be great if we have a system or if we have a teaching structure like country ABC? Is there something you have as a benchmark?
Well, I think with the University of Applied Sciences and our dual programs, we already are set up quite well. So we have a close contact to industry, and we are working together with industrial practices. And about the didactics, we as a university are continuously improving our didactics, and especially in the University of Applied Sciences, the didactic aspects are very important to us. So I think we are quite good on our way, but quantum computing is a new upcoming field. Here we can look at the others and improve our approaches, I'm sure.
Thanks a lot for that answer. And as I look on our watch, we're already at the end. So thank you very much for sharing your insights.